In the previous video, I used relative growth rates to understand exponential models. Here, I'll show you how to use logs to check whether an exponential model is appropriate. Before we jump into this approach, let's recall some earlier facts. At the top, you see two rules for the log function. The first shows that logs convert products into sums. The second rule converts exponents into a product. I've also included here the exponential model, because this will be our starting point. Keep in mind here that little t represents the total time since the stock was first recorded. The idea is to apply the log function to the entire exponential model. So on the right, you first see the exponential model, and then the log applied to both the right and left-hand sides of this equation. Then we can apply the first log rule to split off S0 from the rest of the product. Then in the last step, I've applied the second log rule to move little t over big T out of the exponent. This equation looks complicated, but keep in mind that S0, big T, and R are all fixed values in a given scenario. What this means is we've written log S as a linear equation in terms of t. That is, you can think of this as an equation of the form b plus mt. Here, b, the intercept, is going to be log of S0, and then m, the slope, will be this entire piece. Here's a visual of this transformation. On the left, you can see the graph of the traditional exponential function, with time on the horizontal axis and the stock levels on the vertical axis. Notice that for larger stock levels, the curve is increasing faster. This shows the exponential relationship between stock and flow. On the right, the graph shows log of S as a function of t, highlighting that this is the equation of a line. Let's apply this idea to the fertilizer data we considered earlier. I've included the original data in the first two columns of the table. The third column shows the log of the fertilizer input. For example, log base 10 of 26 is 1.4. The top graph shows the plot of the original data. The data seems to follow an exponential model, but this is hard to eyeball easily. The bottom graph plots the log values. Here, we can see the data points do fall close to a straight line, at least through 1975. Because the log values fall on a straight line, this indicates that an exponential model makes sense for this data. The final value, at 1985, doesn't seem to fall on this line, indicating that the data may no longer be following an exponential model. This is consistent with what we saw earlier when we analyzed the data using relative change. Before ending this video, I wanted to share another example of log graphs taken from the recent news. This graph is from a March 23rd New York Times article. The graph plots the total number of deaths reported due to the coronavirus, measured from the day when the country first reported 25 deaths. For example, China's graph extends the farthest right since it was the earliest country to report 25 deaths. In this graph, the values are plotted by taking the log of the number of deaths, in the same way I graphed the Swedish fertilizer example. The gray lines represent pure exponential growth. For example, the line farthest to the left is labeled deaths double every day. This represents an exponential curve with a growth constant of 100% and a time step of 2 days. Looking at the entire set of graphs, we can compare countries to see how the growth rates between the countries compare. For example, Japan's curve is much flatter than most other countries. This shows that the percentage growth in Japan is much smaller than in the rest of the world, which suggests a more controlled spread of the disease there. Also, we can see from this graph whether the relative growth rate is increasing or decreasing over time. For example, in China, notice the plot is concave down, curving below a straight line. This indicates that the relative growth rate in China has been falling. This graph is updated every morning, so you can look at an updated version by checking the New York Times article. You can also find a state-by-state graph for the United States there. I'll include a link in the Sakai forums.